Okay, now we will discuss one of the very important topic in physics, which is a harmonic oscillator, which may be damped or undamped. So first thing is we will do it analytically, then we will do for the numerical solutions of the solution. So what is a harmonic oscillator? So harmonic oscillator we can consider which is oscillating harmonically. Okay, that's why we can consider a system which has a spring and mass system, which is attached to a rigid body. Then I have to do is I have to oscillate this one. So what you do is I have to pull one side and release it. What will happen? It will oscillate to and fro. Okay, if I try to plot this position and velocity, we get the information about the motion of this system. Okay, so there are two cases for this one. The first one is called undamped harmonic oscillator, where there is no damping is there. So if you are doing this experiment in outside our Earth, what will happen? Here we have a air resistance. If I do this in outside, what do we get? If F is equal to minus K into S, which is a Hooke's law will be the equation for that one. Therefore, we have the equation F is equal to m into d square x by dt square is equal to minus K into x, where K is the spring constant. Okay, which means that K is the force the force is proportional to K. If we have using a spring with a larger spring constant, this force will be very large, and the force is always towards the equilibrium position. Okay, if we replace from here, there's a tendency to come back to its equilibrium position. And if you can rearrange this equation, you may get the equation d square x by dt square. You can come to this one, the left side of the equation. This becomes plus k by m into x. So that is a second order equation. If I solve this one, I get the position and velocity of the equation at any time. Okay, that is a deterministic problem, because you can actually predict what is the position in the future time. Okay, there is a modification in the damped harmonic oscillator to this equation. Last time we have F is equal to minus kx. In this case, we have to add an additional term which is proportional to velocity. So a damping term will be proportional to velocity of this equation. Therefore, we can put a constant also, b minus b into dx by dt. If I rearrange this equation, you get an equation as m into d square x by dt square plus b into dx by dt. This is a velocity damping term. B is a damping coefficient plus k into x, where k is again, this is a spring constant. Okay, is equal to 0. Then you can divide the entire equation by m. Then you get the coefficient b by m, and you get a k by m here. Okay, that's why we get two differential equations. If I solve this one, we get the solutions of these two cases. Okay, so now first we consider how we can solve an undamped harmonic oscillator system. So this is equation m into d square x by dt square plus is equal to minus kx, and we find that how we can rearrange to d square x by dt square plus k by m into x is equal to 0. Okay, this because doing with the this constant will be difficult. I can rearrange with a single constant, which is I put a constant as a is equal to root of k by m. Then what is this become a square into x is equal to 0. Okay, this is a second order differential equation, and it's so homogeneous and linear. So we can use the method we discussed in the previous video, solve it, so that you get the auxiliary equation as m square plus a square is equal to 0. Then you get the solutions m is equal to plus or minus ia. So that's why you can solve it. You get the solution as the solution as x of t is equal to s. Because of the complex number, you get the solution from the table discussed in the previous video. X of t is equal to a sin at plus cos b cos at. Okay, this is the general solution of a undamped harmonic oscillator. For a particular case, we have to, there should be some initial conditions where you are pulling this to this side and relieved, or you are pulling to this side, or putting to how much distance you have pulled is determined by the initial conditions. Okay, you just pull it. The time in which you are leaving is taken as the initial time. T is equal to 0. Then you have to give what is initial velocity and initial position. Then you can determine the final velocity and the final position. Okay, that's called a particular solution. Therefore, we can try a particular solution. Suppose a cart is pulled to the right of these initial conditions. Okay, Suppose that the cut is in, we are rotating this one. I pull it to right side of the position, then leave it. The initial condition is x of 0 is equal to x0, pull to a position x0. Then it have a velocity. Initial velocity should be 0. Then initially velocity 0, then to one side, and this will move. It will increase the velocity on the opposite side. Then again this position, the velocity will be 0. Then it turns its direction. Okay. So these two conditions, I can write it as x of 0 is equal to x0 and dx by dt, that is the velocity 0. Then I can directly put this to here, x0 is equal to a sine, the time is 0, initial time, a0 plus b cos a into 0. Then automatically this become sine 0. This this sometimes might be missing, so this is 0. Then I can write it as my equation become x0 is equal to b, and the second equation is I had to take the derivative. So this is the equation for second derivative, and find the dx by dt. I can take the derivative of sin 80 and cos 80, then I get the second equation. Okay, then I put these two conditions to these equations. I may get that x0 is equal to b and a into a is equal to 0. The first term is cancelling. So my solution for particular case, this is xt is equal to x0 cos 80. x2 is equal to x0 cos 80. Okay, then I can try to plot these equations. This is actually sine 0. You get a sine solution for this one. And you may get the frequencies. Therefore, this is called angular frequency. And omega is actually, this equation is not written in terms of omega. Actually, this term a square is actually, you can take it as angular frequencies. Therefore, angular frequency square. From this equation, I can directly get it that this is root of k by m. That is determined by your spring constant and the mass of the system. Okay. Then we go for the what happens if we are adding some damping to the system. Okay, so what you have to do is the equation is m into d square x by dt square plus b into dx by dt plus kx is equal to 0. Then I can divide the entire equation by m. Then I get a b by m and a k by m. Then I can rearrange this equation by a new constant, which is gamma, and the second constant is omega 0. Okay, so I get two constants. So this is a rearranged equations. Then I can use the second order linear homogeneous equation solutions discussed in the previous video, so that I get the, so I can use the equation minus b auxiliary equation, write the auxiliary equation first. Then I have to use the quadratic equation solution by minus b plus or minus root of b square minus 4ac by 2a. Then I have to find the solutions. So this is a characteristic equation, which is r square plus 2 gamma r plus omega 0 square is equal to 0. Then I have to use the quadratic solution. Then I get the r is equal to minus b plus or minus root of b square minus 4ac by 2a. Then I can cut down some of these constants. Then minus gamma plus or minus root of gamma square minus omega 0 square. Okay, the nature of this root is real, complex, and repeated, determined by the behavior of the system and form. So according to what is this form, this equation, gamma square minus omega square, we get a different type of solutions. There are three possibilities that we discussed in the next slide. Okay, so this is our solution for this damped harmonic equation. R is equal to minus gamma plus or minus gamma square minus omega 0 square. We can first consider whether this constant gamma is greater than omega 0. Gamma is greater than omega 0. So then we can, in this case, the damping force is strong and system returns to equilibrium without oscillating. So if we have the solution for this equation become x of t. So the r1 and r2 we can determine it should be real, distinct, and negative. Real, distinct, and negative. Then you can go for the table discussed in this previous video, that you can find that it is these are the two solutions. Then if you have r1 and r2, the solution is x of t is equal to c1 e raised to r1t plus c2 e raised to r2t. Okay, then c1 and c2 are again, it's a constant. Then since it is a negative, and this is a combination of two negative number which is exponential, c1 e raised to, this is a negative value and this is again negative. And if you plot this one, you get a exponential. So the x is varying with the time. It's an exponential combination. This is a combination of these two. Okay, this is called a damped harmonic oscillator with over damping. We go for the second case. If it is gamma is equal to omega 0. If gamma is equal to omega 0, what will happen? This term will be cancelled. Then your R will become, you have to take the root, then you get minus gamma. This is equal to, R is equal to minus gamma. Then these are the two roots which are equal. So again you cover the table where we have a real unique roots. Two roots will be there for the second order equation. Then you can directly get the table from the table. It is the solution is x of t is equal to c1 plus c2 2 into raised to minus gamma into t, where c1 and c2 are a constant. Okay, if you look at this picture, there are three cases I determined. It is shown here. So this is over damping. Then the second one is called critical. I mean, the critical damping will come lower to this one. It will be coming like this. Okay, this will be like coming like this. This is also an exponentially decreasing term, but the level it is going from higher to low will be different from the over damping. Okay, and finally we have which is called under damped case. This is an interesting one where we have a gamma is equal to less than or omega 0. Then what will happen is this term become a complex number. This term become a complex number, minus gamma plus or minus I into root of omega 0 minus gamma square. So what you get is your R should be a complex number, minus gamma plus or minus omega d. So from your table you can consider that this is R is equal to, you can put this is alpha and this is your this is alpha and this is your beta. Then this become a into e raised to alpha t. This alpha become minus gamma and cos omega t plus c2 sin omega d into t. This means your beta is omega d, that you can substitute here, and this is the general solution of an undamped harmonic oscillator with the under damping. Okay, if you look at the solution, there are two terms. One is called exponential decreasing term, another is called a sinusoidal and cosine term general solution, which means that there should be some oscillating case. And if you apply this initial condition to the system, you can it may be one of these solutions will come, maybe with either sine or cos. Therefore it contains a sinusoidal solution as well as a term which is called exponential decreasing, which means that the oscillating solution with the frequency omega, angular frequency omega, will decay by the second function, which is e raised to minus gamma t. This is actually simple to, if you look at this graph diagram, you can see that if there is damping, what will happen? The amplitude will decrease over time and it will come to like this. So if you plot the displacement versus time, you get the same graph you are showing here. Okay, so that is determined with the damping effect, whether it is a spring constant, so the damping spring constant, as well as the environment you are doing this damping will determine whether it is a over damping, under damping, or critically damped oscillations.